Department of Mathematics and Statistics, Central University of Punjab, welcome you all on the behalf of Organizing Committee of FDP. It is the 10th day of 2-week faculty development program on data science and scientific computing. We hope you have been gaining valuable insights and experience throughout the journey.
Our today's session is taken by Professor Amandeep Kaur ma'am from Department of Computer Science and Technology, Central University of Punjab, Bathinda, on the topic Deep Learning and Neural Networks. Before starting our today's technical session, we would like to invite today's chairperson, Dr. Durvesh K. Verma sir, Assistant Professor, Department of Mathematics, Miranda House, University of Delhi, for formal introduction of our resource person. Over to you, sir.
Thank you. Very good morning to everyone. And today's topic on deep learning and neural network by the Professor Amandeep Kaur. Before starting the session, the brief introduction for the speaker. Professor Kaur is Bachelor in Engineering and M.Tech and PhD in Computer Science and Engineering. And she started her career from the Adesh Polytechnic College in 1997. And then she worked nearly 4 years for the Center for Development Advanced Computing Mohali. And then she has worked as project officer and then worked as senior engineer and design engineer. Later, she in 2005 joined Punjabi University Patiala. After contribution of 10 years in Punjabi University Patiala, she joined Central University of Punjab as associate professor and working as professor from 2018 onwards. She has already guided 6 PhD students and currently 4 students pursuing their PhD under her, and more than 60 M.Tech dissertations. She has published many research papers in the Journal of International Repute, and she is also presented papers and delivered talks in conferences and published paper in proceedings. Currently, she is holding the post of head and professor in the Department of Computer Science and Technology, and she is also worked as dean. She is former dean, and his area of teaching is working is soft computing and artificial intelligence. In addition to, she is contributing as in charge of the computer center at Central University Punjab and also the warden in hostel for the Central University. Now I welcome ma'am for the session. Thank you, ma'am.
Thanks for introducing me. So I'll just share the my presentation and we'll start with the lecture. So please enable, I can share my screen. It has been disabled. So I'm not able to share the screen because I think I'm not given that right.
Ma'am, you are co-host now and you can share the screen. Please check it.
Okay, thank you.
Perfectly visible, ma'am.
Okay, so we'll start with this very interesting topic of neural networks and deep learning, and then we'll see how it can be implemented using a Python library, that is PyTorch, can be used. So before we continue with the artificial neural networks and deep learning methods, I'll just very briefly we'll introduce what is meant by neural networks, and only then we can shift to the coding part which is there. This concept of neural networks have come from the brain metaphor, ki how our brain works. We have a large number of neurons which are interconnected, and they pass some signals. And as we learn, those connectivities become permanent. So initially, they tried to design a neuron, ki how it works. And in 1950s, it all started, and they were trying to implement an artificial neural network. So the concept of developing artificial neural networks, it started with the understanding of our own neuron, how it works. So we have synapses, dendrites, axon, and output. So the sensory data is being captured, and then that is multiplied with some weights, you can say, and then there is a central processing unit out here in the neuron, and you get an output. This output helps to trigger the next neuron, and when this triggering is done again and again, these links become permanent. That is what we call as learning. So from this concept of biological neuron, they tried to develop an artificial neuron. So that all came from our own, you can say, nervous system. Now, when we define neural networks, that is, we have small processing units. They have the same structure, and they all are interconnected, and they are capable of working in parallel. So the main strength of neural networks was that it can provide us parallel computation, but when we are simulating it on normal machines, naturally it will be sequential. But when there are some ICs which are hard-coded, and so the speed benefit will be there, and tolerance will be there, because instead of one very strong processing unit, we have a large number of small neurons, or you can say small processing units with very simple structure, and they together are leading to a very high-end processing. So in this, the main concept of artificial neural networks is that the information processing occurs at many simple elements that are neurons. So signals are passed from between neurons over the connection links, and these connection links will be associated with some weights. So any input which is coming, it is multiplied with the weights, and at a neuron, you get the net value when you sum up all these weighted inputs together, and this is passed to an activation function, which gives the final output. So each neuron applies an activation function to its net value to determine the output signal. So any neuron will have this same kind of working. So you can say, when we say the neural network is getting trained, basically we are changing the weights. So the information about any problem is saved in the weights of the neural networks. So how these neurons are interconnected to each other. So this is a biological neuron, and this basically is an artificial neuron. So interconnection of a large number of such neurons will lead to different neural network architectures which are there. So in this case, these are the inputs, and they are multiplied with some weights. So in this neuron, there will be a summation unit, and you get a net value here. This net value is given to this activation function, and you get an output. So you use any kind of a neural network, its basic working will be the same. The only thing which is going to change is how we train these weights, how we change these weights, so that when I give a specific input, I get a correct output, right? and what kind of activation function I'm using here. So we are capable of changing only the weights and the activation function, which we can specify. So you train any kind of neural network, the general learning will be taking place by changing these weights. So there are many neural networks. What should be the initial weights given to these? How these neurons are interconnected with each other. So based on that, we have different types of neural networks. We have feed-forward neural networks like multilayer perceptron or backpropagation. We have recurrent neural networks where some kind of feedback from the output is again given back to the input, like counterpropagation neural networks. So basically, we have given different names to these neural networks based on the type of training which is taking place and based on their topology, you can say, how those neurons are interconnected. So we have different types of neural networks. So there are some basic concepts when we are training it on one input, the weights are getting changed, we are getting the correct output. Then we are taking the second input, we are again modifying the weights so that we get the second correct output. But it should not be like that, when it is getting trained on the second input, it forgets the first. So it should be able to recognize the first also, when first input is given, it should give the correct output. When I train it on second, when I give second input, it should give the correct output. So this capability of the brain is called plasticity, right? And stability. And plasticity is it learns newer things, but does not forget what it has already learned, the past. So there are two concepts in neural networks. One is the stability, that is, it should not forget what it has already learned when it is learning something new. And thus, the stability and plasticity issue is of great importance in neural networks. So we need to retrain the neural network with the changing environment. And it needs to be receptive to the newer information while retaining the older information. So these are some of the concepts which are there. So the focus, when we see the neural networks, the main focus was how we are going to train those weights, how we are going to change those weights so that we say the neural network has learned. So different researchers have put up different methodologies, learning laws. Right? So Hebb has given the learning law, Minsky has given a reinforcement learning. So now we have reinforcement neural networks also. Okay? So there are different learnings which are there. So like Hebb has stated that neurons that fire together, they wire together. So one neuron's output is going to the next and triggering it. So if first is on, it makes second also on repeatedly. Then we say that they are wired, the connection becomes permanent. So when we are learning something, if we do something again and again, it is hardwired in our brain. So the same concept is being taken for artificial neural networks, like reinforcement learning. So trial and error learning. So if we are working on something and we do it correctly, then you are rewarded. If you do it wrongly, then you have some penalty on you. So that concept has also been taken by artificial neural networks. So now when we define artificial neural networks, basically they consist of large number of simple, highly interconnected processing elements which are inspired by the structure of the brain. So this is a single neuron and they are interconnected. So the most important thing, like I've said, one is these weights. So there are different training algorithms to train these weights. But the first problem is what should be the initial weights? How we take these initial weights? So they also vary from algorithm to algorithm. In some of the algorithms, these weights are considered to be same. In some, they are taken as random. And after that, there are training algorithms to train them. And one of the most important thing is this activation function. So if you're using some linear activation function, then it is simply a single layer neural network where we have only one processing layer. So we will see what it means. So you have different simple thresholding. This is a linear activation function, which is normally used in single layer neural networks. So first of all, we will see, initially we had single layer feed forward neural networks when there is no feedback going back. We had multi-layer feedback forward networks, feed forward networks. That means there are multiple layers, again there is no feedback. And we have recurrent neural networks in which there is some kind of feedback going from output to inputs. So these are the three types of architectures, you can say, which we can have. So as we have seen that the neural networks, they all have the same processing elements. They all need to train their weights, but there are different algorithms for training of these weights, and they can have different topologies based on how those neurons are interconnected with each other and what kind of activation function these neurons are using. So neural networks, they learn by example, like our brain. So that is basically supervised learning, you can say, right? So I'll show apple and I say ki this is apple. So we learn ki this fruit is apple. In the same way, to the neural network, we'll give the example ki this is the input, then this should be the output, and it learns. So this is one kind of learning in neural network, that is supervised learning. Another kind of learning could be ki you give me some pencils, maybe of 3 colors, and I ask a child to separate them out. Maybe the child won't even know ki one is a purple color, other is pink, and other is yellow. But seeing them, he or she will be able to put them into different categories, group them into 3 different classes based on the color. So even that is unsupervised. We are not giving any training data set where this is the input, this should be the output, but we know things which are similar should go into one group. That is something which is called clustering, which is there. So we train with known examples. Once trained, they can be used to solve untrained instances of that problem. So if I use a neural network to recognize the faces, or I want to mark biometrics based on face, so for all the employees which are there in the department, I'll take their face images and I'll show it to the neural network if this image belongs to this employee. So next day, when that person is registered, he or she comes for the attendance, it will capture the face image. And from this untrained instance, it will be able to mark the attendance. So common categories of training algorithms are, like I've said, supervised, unsupervised, and reinforcement. So depending on the kind of problem we are working on, we can use different types of trainings. So these are the different training algorithms which are there. So now briefly we'll see how it all started. We started with the single layer neural networks. So in this, basically these are the inputs, and this is called the input layer of the neural network. So these neurons are not performing any kind of processing, but what they are doing is what input is given to this neuron, this is being distributed, or this is being connected to all the neurons in the next layer. And this is a single layer of processing neurons. So all the processing which we've seen, summation unit and activation function, those functions. So this is only a single layer of processing neurons. And such a neural network is basically called a single layer neural network. So you have an input. So this input multiplied with some weight goes to this neuron, multiplied with another weight goes to the second neuron, and similarly to all the neurons in this next layer. Same is true for all the inputs. So here, inputs into the corresponding weights will give me the net value. This net value is given to activation function. In single layer neural network, it is normally a thresholding function. If the net value is less than 0, maybe then it is 0. If it is more than 0, then it is 1. So this kind of neural network was a single layer neural network. There is no feedback going on. This is a feed forward neural network. And this single layer neural network was called a perceptron. So it worked generally with the binary inputs and outputs. And training it was easier. So we will see how we can train a single layer neural network. So single layer neural network basically consists of 2 layers. One layer is non-processing and only one output layer, that is the processing layer. It is acyclic in nature because it is feed forward. There is no feedback. So simple perceptron, as I've said, you get the output in terms of ones and zeros based on the net value if it is greater than 0 or less than 0. So net is inputs into weights. So this is a simple algorithm to train the perceptron. So I have said that neural networks is all about changing the weights in such a way that when I give a specific input, I should get a specific output. So you have only 2 operations which are performed, that is multiplication and addition. So you have summation unit and weights. You have inputs into weights. So a simple perceptron training algorithm, how it works. So you have a training set where you have a given input and you know that this should be the output. So when you're training it, you will give the inputs, you will check the output. So if the output is correct, then you don't need to change the weights. So the weights in the next iteration, they are same as the previous. So if the output is 1, but it should have been 0, then the weights are decreased on the active input link. Okay. So ij is like we are taking neuron 1 in the input layer is connected to neuron 1 in the output layer. So this is ij is 1, 1. So this neuron 1 is connected to neuron 2 in the output. This is wij is 1, 2. So if my input, this is 1, 0, 1, and the output here should be 1, and it is coming also 1, then I don't need to change W1, 1, W2, 1, and Wn, 1. Right? But if I should have got 1, but I am getting 0, then with all these weights, what I'll do is, so I will reduce these weights. So minus alpha into xi, where xi is the input which we are giving. And if the output is 0, but it should have been 1, then we will increase the weight, that is plus alpha into xi. So now this alpha is basically it is the training rate, you can say, which we have. So it can have any value between 0 and 1. So now when I see an example, so initially when single neural networks were designed and the training algorithm was developed, so the most important thing was changing the weights. So everyone was very happy and they felt that many pattern recognition and other typical problems, which as humans we are able to solve very nicely, but which are very difficult to write handcrafted algorithms to solve that problem because of the complexity. Then Minsky was one of the researchers who has shown in his work that a single layer perceptron is not able to solve a simple problem like XOR gate. So it is able to solve the AND issue, because in ANDing what is happening, you can take the inputs as 0 or 1 or bipolar as -1 and 1. So if we consider an AND gate, -1 and -1 should be -1. So all these three combination -1, 1, 1 and -1 should be -1, and 1 and 1 should be 1. So this are one type of outputs. If I give any of these inputs, my output should be -1. And when I give this input, my output should be 1. So this kind of output, we are able to separate. If we have 2D inputs, that means 2 inputs, we are able to separate it with a simple line. And same is true for OR also. So for OR, for the first only -1, -1, it is -1 output. For rest, it will be 1. And we are able to separate out the 2 types of outputs for this specific inputs by using a single line when we have 2D data. So if we have 3D data, we can separate it by a plane or some hyperplanes. But if I consider this example of a XOR, so and now XOR means -1, -1 is -1, and 1 and 1 is -1. If we see their truth tables, and -1 and 1 and -1 are 1, 1. So X and X are one type of outputs, and this O and O are the other type of. This is class 2. So you draw a line anyways. So if I draw a line here or I draw a line here, I'm not able to separate out the 2 types or 2 classes of outputs. So if I draw a line here, there is X here and O is here. If I draw a line here, there is one X on this side, the other X on the other side. The same is true if I draw in any of these directions. So this problem is called the problem of linear inseparability problem. So he was able to prove that we are able to handle only those problems using a single layer neural network which are linearly separable. If they are not linearly separable, we won't be able to okay, so I'm getting some messages in between. There was this, kindly tell us how to fix W1 and W2 in the previous slide. So we will be talking about that only in next few slides. So one of the candidates is not able to hear me. So kindly let me know if you all can hear me or I need to change something.
Ma'am, you are audible.
Okay, thank you.
You're audible, ma'am.
Okay. So in this case, we are not able to train a single layer neural network if the problem is not linearly separable. So for many years, there was very little research in neural networks, you can say, because they did not know how to solve this problem of linear inseparability. And later on, they realized that this problem can be solved by using, instead of using a single layer neural perceptron or neural network, using multi-layers with non-linear activation functions, we'll be able to solve this problem. So they were trying to develop multi-layer neural networks. But in that case, the issue was that there was no algorithm to train the weights of multi-layer neural networks. And if in the previous slide, like one of the candidate has asked how we are going to change these weights. So in this problem, what I can do is I can select these weights randomly. Right? Like I can keep it, this is 0.25, maybe this is 0.5, this is 0.75, and this is 1, 0, and 1. So we multiply it. So this is 1 into 0.25, this is 0 into 0.5, this is 1 into 0.75. So 0.75 plus 0.0 plus 0.25 gives us 1. So this total value of net is 1. So 1 is greater than 0. So this neuron becomes 1. So in this ways, initially we take the weights as random, and then we keep on changing the weights, increasing them or decreasing them till we get the correct output for the input. So as I've said, for solving this problem of linear inseparability, what we need to do is we need multi-layer neural networks with nonlinear activation function, and we needed some kind of training algorithms for these neural networks. So now we will see how we can train XOR by using an additional layer in between the input and the output layer. So in this case, this is the input layer neurons. They are non-processing, you can say. Their only work is to distribute the inputs which are coming to them to all the neurons in the next layer. So these are the 4 kinds of inputs which we are giving. So this is, you can say, a hidden layer. So between the input and the output layer, there could be one or more than one hidden layers. So we were able to train the weights between input and output layer because in that case, we knew the difference between the actual and the target output. And this was the error based on which we could train the weights. We could either decrease the weights or we could increase the weight. So this alpha, which we had taken, this was basically in this case, this is delta, which we had taken. So this is the difference between the actual output, which we get after applying this input to these weights, and we get output, and this is the target value. So for a single layer neural network, we knew that for the neurons, the input neurons, these are the inputs, and this is the output neuron, and this is the output. So we knew the input and we knew the output, desired output, that is the target output, and the actual output, which we get after applying the inputs to these neural networks. But when we are using this hidden layer in between, for this hidden layer, we are getting some inputs here, and it is giving us some output, but it does not have any desired output or the target output for the hidden layer. So we don't have any target output for the hidden layers. Okay? Then how to train it? How to change the weights based on the difference between the actual output which is coming and the target output. For single layer, we knew the target and we knew the actual output. So that was the issue in training the weights between the hidden layer and the output layer. So this was solved by a training algorithm that is still being used, that is the back propagation neural network. So it had given us a way of training the weights connected to the hidden layers. So if I see here, so this XOR is now trained, or we'll say see if it is giving us the correct output or not. So first of all, I apply input as -1 and -1 here. So when I'm applying -1 and -1 here, this is -1 into 2 will be -2 here. And this is also -1 and this weight is -2. -1 into -2 is 2. So out here the net value will be at Z1 will be 2 minus 2 plus 2, that is 0. Now the threshold value for this which I've kept is 1. So if my net value is below 1, then I will consider 0 as the output of this neuron. If it is higher than 1, then I'll consider it to be the output to be 1. So this is -2 plus 2, that is 0. So this net value is less than theta 1. So I take this output as 0. Right? Or if you're taking this binary, you can also consider it as -1. So I take the output as -1 in this case. Right? So again, I take it for Z2. So this is -1 into -2. And this is -1 into 2. Again, we are getting the same. Net value is 0. So I can get -1 here. So now out here, the threshold which I am considering for as an activation function is the theta is 0. So if your value is less than 0 or equal to 0, your output is -1. Otherwise, it is +1. So here, now I have -1 into 2 plus -1 into 2 is -4. Now this value is less than 0. That means your output is -1. So in the case when I have the inputs as -1, the output is -1, and the same I'm getting here. So it is giving me the correct output. Now we check it for the next input, which is there, that is -1, and so this is -1 and this is 1. So again, I take for Z1, net value I want to find. So in this case, the net is equal to -1 into 2 plus 1 into -2. So the net value which I'm getting here is -4. And my threshold value here is and my threshold value here is 1. So if the net is less than 1, then it should be -1 here. So the output value for this net value is -1. So in the same way, so this is output is -1. So same way I check it for Z2. Z2 net value in this case, -1 into -2 plus 1 into 2. So this value comes out to be 4. So again, the threshold value is 1. So if the value is more than 1, here I will be getting output as 1. So this output is 1. So now these are the outputs of the hidden layer. But in this case, there is no desired output which is there. So there is a different training algorithm for these weights which are between the hidden and the output layer that is done through backpropagation algorithm. We'll see it in the next few slides. So now when we compute the net value for y, so it will be -1 into 2 plus two into 1. So the value is 0. So if I take, so we'll just see in the previous slide how we are taking this threshold value. So 0 is here. So we can take if net is less than 0, then the out is -1. If net value is greater than equal to 0, then the output should be 1. So in this case, it falls into the second. If we consider this condition, if net value is greater than equal to 0, the output should be 1. So if we check it for this second one, so the output is 1. So in the same way, we can check it. And now we are able to prove that instead of using a single layer perceptron, if we are using one additional hidden layer in between, we are able to separate out or we are able to solve this problem of XOR. And the whole concept, you can say, till we reach the deep neural networks, focused on this. As your problem becomes more complex, you need to add more hidden layers in between your input and output. So as you add more hidden layers, it is able to separate out the different types of outputs which are there. So this whole concept is that if you add more hidden layers with the nonlinear activation function, it will be able to solve the complex problems which are there. So initially, this is after the training, this model we got, these weights we got. And for this neural network, what we are going to save is the weights between input and this hidden neuron, inputs and this hidden neuron and the output neuron. So that is how we save the trained neural model. We are basically saving the weights, fine? And so we can make use of it. So like I've said, one is adding more hidden layers and second one is instead of just using a linear thresholding function, we need to use some non-linear activation functions. Okay? And so they have their own, because we want our neural networks to be stable and we want them to be plastic also. So sometimes they won't train if we won't consider this non-linear activation function. So sigmoid is one of the most, you can say, widely used, or initially it was used in backpropagation due to certain advantages it has. So now we are not taking net, we are not comparing it with the threshold, but the output is 1 by 1 plus e to the power minus net, where net is computed as inputs into weights. So this function gives low values for negative and high excitation levels. So what basically it does is when you have, it becomes stable. That is, as your input value goes on increasing, it won't continuously keep on increasing. It will stabilize to 1. So after a certain value of 1, its value will become 1 and it won't increase more than 1. And similarly, for negative values, as they keep on increasing, it becomes stable near to 0. So in this case, as I've said, this is the training rate, alpha 0.1, alpha 1, alpha 2. So how it is getting trained. Right? So this shape of sigmoid function keeps on changing. So in this case, it will be dependent on alpha values. So this is one function which is commonly used as a nonlinear activation function. Now there are many more, like in deep neural networks, we are using ReLU because its complexity is higher. Right? So it takes some computing time. So for every neuron, we have to compute its output value based on this activation function. So if this is complex, it will consume more computational power. So we want a simpler nonlinear activation function, or sometimes we convert a non-linearly separable problem to linearly separable problem before further processing it. So there are neural net RBF is there, radial basis function. So those things are there. So this activation was used in backpropagation because it has a simple derivative which can be found very easily. So this was preferred, and at very low or very high positive excitations, its value becomes stable near 1 or 0. So otherwise what will happen? All your neurons will become active, because if this value keeps on increasing, the output will keep on increasing. When this output is given to the next neuron, that neuron will also trigger, and it will give still higher output. Then again, it will go to the next neuron. So all the neurons will be triggering. So the training won't take place as we desire. And there is another thing which is being used, that is the neuron bias. So you have the input neurons. They are distributing the inputs, and then the input is multiplied with some weight and given to the next neuron, and that neuron has a summation unit. So with this inputs, there is a specific input which is always 1, but its weight can be trained. So if we see the graphical representation, how this bias works, and then this net value is given to the activation function. So the effect of this neuron bias will be, if your sigmoid function is 0.5 at 0, now it is shifted by W0. And what is W0? W0 is the weight of this bias input. So as you change it, its location is, it is getting transferred. So that is the effect of introducing bias in your network. So biased neuron learns even such input vectors that a non-biased neuron is not able to learn something. So if you just give the inputs and not the bias input, sometimes your neurons won't train. So we come to the conclusion that the additional weight cost, because there is one extra weight which we need to train, there will be more calculation, but it improves the neuron properties. So it is used with the neurons. So you have hyperbolic tangent, depending if you have bipolar input outputs, instead of sigmoid, you will use the hyperbolic tangent. So now, briefly, we'll see multi-layer neural network backpropagation. As I've said, initially the issue was that they knew that the problem of linear inseparability could be solved using multi-layer neural networks with multiple hidden layers in between the input and the output layers with nonlinear activation function. But there was an issue because in perceptron, we were taking the difference between the desired output and the actual output to retrain the weights. But for the hidden neurons, there was no such desired output, which we knew beforehand what should be the desired output at a specific hidden layer neuron, so that we can compare the actual with the desired to take the difference and accordingly adjust the weights. So the backpropagation algorithm was given to help to train the hidden layer neurons. Okay? So this is a multi-layer neuron inputs, first layer of processing neurons, second layer of processing neurons, and maybe third layer, and that is the last layer is called the output layer. So this is just, so now we see how these we train the weights. So in backpropagation, we start from the output layer and the last hidden layer. So if it is the last hidden layer and this is one specific neuron from there, so first we will train the weights between the last hidden layer neurons and the output layer neurons. So neuron A is a hidden layer neuron, neuron B is the output neuron, and it has a weight of WAB. So first we apply the inputs to the network and find out. So initial weights, as I've said, they will be some random numbers. Next, we find out the error for neuron B. So as I've said, the error for neuron B is the derivative of the sigmoid function because it uses the sigmoid function for computing the output value, and the derivative comes out to be out B, which is the output for actual output for B, 1 minus that output. So just a moment. So this out B into 1 minus out B is basically the derivative which we get based on that activation function into target B minus out B. That is the desired and the actual difference between the two. Out into 1 minus out term is necessary in the equation because of the sigmoid function. If we were using a threshold neuron, it would have been only target minus out. Like for perceptron, we are only taking this difference. Now we are using a nonlinear activation function. So the derivative of the nonlinear activation function comes out to be this. So this is the error term which we get. And this error helps us to change the weights. So WAB, previous weight plus error B into output of A. The output of A is going as input to B. So basically this is the input to B, which is coming as output from A. So we are able to change the weights of this last layer, that is the weights between the output layer and the last hidden layer. So we update all the weights in the output layer in this way. And now, how do we calculate the error for the hidden neurons? Because we don't have the target for it, as I've said. So we backpropagate them from the output layer, and that is where it gets its name. So this name, backpropagation neural network, comes from this only. For hidden layers, we don't have any target output. Because of that, we are not able to directly compute the error for changing the weights, but we will be indirectly doing it. We will be taking that error from the output layer and using it to train the weights between the hidden layers. So for example, if neuron A is connected as shown to neuron B and C in the output layer, so there is error be between for weights AB and for weights AC. So error in neuron A is computed as output A 1 minus out A into the, now it doesn't have any direct way of target minus the actual. So we are taking the errors which we computed for the hidden layer. So in this way we get the error for A, and this can be used for training the weights between the last hidden layer and the next hidden layer backwards. So, and this process is repeated till we reach the input layer. So, backpropagation algorithm gave us a way to train multi-layer neural networks. So, with this, there again the emergence of neural networks took place, and now we have reached till deep neural networks, which are using large number of hidden layers in between the input and output layers. So finally, with this brief introduction, we started with single layer neural networks. They had their problem of linear inseparability. And because of that, for problems where we could not separate out the outputs as linearly separable, so for that we needed multi-layer neural networks. For multi-layer neural networks, we did not have any training algorithms because there was no target defined for each hidden layer. We only knew in our training data set, we only know that these are the inputs, these should be the final outputs. And further, we needed some different activation functions, nonlinear activation functions for them. So from neural networks to deep learning. So this is images from ImageNet. It has a large number of images, maybe from 1,000 different types of images, and each has a specific number in that. So many applications, they require automatic extraction of refined information from the raw signals. So deep neural networks, as we know, it is able to solve many object recognition, pattern recognition problems, for which the handcrafted methods are very difficult to develop, and they will fail somewhere. So if I write a program to recognize a chair, I'll find some features, but if you see, all these are different types of chairs or sofas, but their shapes are quite significantly different from each other. So what kind of information should be extracted from these raw images, which is common for this class? So if we do it by handcrafted methods, we will maybe use different feature extraction methods. Maybe I want to find out their Zirnaic movements or their shape features or their texture features. But those features, there will be lots of variations between those features also, because these, as we can see, these images are very different. So initially, how we worked with machine learning algorithms, or simply classified. How we did, we took the images, we tried to find some features, and then the simplest way of doing it is we get those features, and then, like, I have a class chair, so I will extract some features from different images of chairs, and I'll take the average of those features. I save it in the database. I get a new image. I want to find out if it is the image of a chair or not. So I will find the same features for that. And now I will take the Euclidean distance between the saved features and the features which I calculated. If the difference is low, I will say that this image also belongs to the class of images of chairs. Otherwise, I'll say that it is not a chair. But we need features which are rotation invariant, which are scale invariant, which are translation invariant. So any kind of features won't be that generic. So we had lots of features in spatial domain, in transform domain, angular radial transforms, polar harmonic features. We could, various texture features like LVPs. But for all those handcrafted algorithms, how many conditions we are going to put? Because the variability is very high. And this problem is solved when we are using the deep learning methods. So the deep neural networks, we say they are end-to-end classifiers. What we need to do, we give the input images and it will train to give us the correct response to that. So it will find a large number of features, extract relevant, refined information from these raw signals. So the extracting semantics automatically requires a model of extreme complexity, which cannot be designed by hand. So this is what I was trying to convey. So techniques used in practice consist of parametric models. So we developed some deep neural network models, and it has a large number of parameters which need to be optimized and making it work on the training data set. So in the brain, similar to the biological system, brain structure is DNA encoded and parameters are synaptic weights which are there. So they are tuned through experience. So deep learning encompasses software technologies to scale up to billions of model parameters and as many training examples, large number of training examples when we give, it is able to train, and it gives a very high accuracy compared, you can say, to the handcrafted algorithms on which we were working for image retrieval and things like that. So there are different popular deep learning frameworks when we talk about Python. So like from Facebook, TensorFlow from Google, and we have many more in this case. So in the present, we will see an example with PyTorch. So this is a normal feed-forward multi-layer perceptron, you can say. You have an input layer and you have hidden layers. So in this case, what is happening? All these input neurons or inputs are given to each of this hidden layer neuron. And the output of each of this hidden layer neuron is given to the next layer, all the neurons. So we know it's good to learn a small model. This is a fully connected model. So do we really need all these connections? So this has been changed in deep neural networks. So only the last layer is basically fully connected. Initially, they are not fully connected. So we see how it, so can some of these weights be shared? That is the question that will reduce, you can say, the interconnectivity and the complexity of the system. So from this whole image, maybe I want to search for this beak. So this pattern is much smaller than the whole image. So for finding it out, we don't need to compare it with this whole image. We only need to compare it with these sub-images and to find a match to get this beak. So we need can represent a smaller region with fewer parameters. Okay? So these concepts are being considered. So there is some redundancy, so we can compress them. And what about training a lot of such small detectors, and each detector must move around? So what we take is, we take small detectors and they move around in the image to find that pattern. Okay? So these are two images. So upper left, beak detector. So this is moving, and then it is able to find wherever this beak is there. So what they're trying to find, they're trying to find the beak. So the same weights can be used here and the same weights can be used here. So we don't need to retrain and change the weights. So this is called the sharing of weights. And this is how we get the concept of convolutional layer. So when we talk about images or 2D data of any kind, we normally use convolutional neural networks, CNN. So it has some convolutional layers which are able to extract some features. First, it will be able to extract some low-level features. In later layers, those features will be combined to get some high-level features. So a convolutional layer has a number of filters that does convolution operation. So we had already seen convolution operation if we talk about images or some kind of a signal. In signal processing, we studied if we want to convolve one signal with another, we get a mirror, 180 mirror image of one signal, and that will be moved on the other signal. The operations will be same. There will be multiplication and addition to get an output signal. So when we talk about image processing, in image processing, the convolutional operation, if I say on these pixel values, it will be performed. So if my kernel value or my filter is 3×3, so what I will be doing is, so this, if I place it on this first pixel, some part of my filter will be outside. Okay. So this is the first pixel. Here, my mask values are overlapping with the pixels, and here they are outside. So there is some concept of zero padding or padding. So this is one way of doing it. Or simply, if we talk about, I can start, instead of, if it is a 3×3 filter, I can start from this pixel. So then I can start from here. Right? So this is the center pixel which I need to process. So this will have some weights, W1, W2, W3, and so on. These are pixel 1, 2, 3. So the same operations are performed, pixel value into W, P1, W1 plus P2, W2, and you get a summation value. And whatever summation value you get, you replace it here. Okay. So this is the convolution operation. Next, you want to process the next pixel. So what basically you do is, now you move this filter by one pixel row wise. So now we will be able to process this pixel. Then you again move it by one column, and you process the next pixel, and so on. So pixel by pixel, we move it column wise, and then when we are able to process all the columns in a single row, then we shift to the next row. Again, this masking or filtering is applied. So this concept is called convolution operation. And we are able to smooth the images by taking different kinds of mask. You can say you can have a mask for smoothing the images, sharpening the images, finding the edges. So these values will change. Like if I have a filter here, 844, these are the weights, these are 2, 2, 2. And out here it is 8 plus 8, 22, 32. So this gives me a weighted average smoothing effect. So there is noise in the image, it will be removed. This is also called Gaussian filter, because if you see the shape, it is like this. It can be extracted also. If I want to sharpen the image, I will have a different kind of a filter. Maybe I will use something like, this is -8, this is 111. So for my smoothing filter, if I sum this up divided by this, 32 by 32 is 1. So its output is 1. And for sharpening filter, if I take, this is -8 and this is +8. So the difference should be 0. In the same way, if I want to find edges in the image, I have different filters like -1, -2, -1, 0, 0, 0, 1, 2, 1. So we needed different kinds of filters, you could say, to get different kinds of information from the image. And that was done with handcrafted algorithms. But in convolutional neural networks, you derive all those filters, you are able to train the neural network in such a way that if you want to detecting the weights, these mask weights will automatically keep on changing till they are able to recognize it. So there will be a large number of filters which will be extracting some features from the image and giving it to you. So this is the convolutional layer. So if you have a 6 by 6 image, you have filter 1 and filter 2. So these are the network parameters to be learned. So they will keep on changing these values, 1, -1, and so on, till it trains to give you some, extract some useful features from the image. So each of these filters will be detecting some kind of a pattern from your image. You want to find diagonal ones, you want to find all these ones here. So you have these filters which will be able to find it out. So this is your convolutional layers. So if you apply filter 1, dot product 3, okay? So -1 माइनस यहाँ पे 0 है तो ये 0 हो जाएगा. 1 into 1 plus 1 into 1 plus 1 into 1 is 3. So you get a 3 here. This is stride 1. Stride 2, you move by 1. So in deep neural networks, strides means you can move 1 by 1, column wise and row wise, as I've said. Or you can take larger strides, like you can leave 1 pixel in between by 2. Your stride could be 2. That means that will reduce the calculations, right? But maybe affect the accuracy. If you come on the next, so these are all zeros. This is 1 and this is also, if you put this filter here, so this is 1, -1, -1. This is -1 into 1. This is 0 and 0. And this is also 0. And this is -1 and this is +1. So the net result will be -1. So so now, instead of 6 by 6 image, you are getting 4 by 4. Why is it so? Because this is a 3 by 3 filter. So you started from, after leaving 1 row and 1 column, you started from here. If you could have done 0 padding, you would have got 6 by 6 image. So this is, you're getting through, by convolving this filter, you're getting some information. So now if I want to find where there are 3 diagonals in my image, so the highest value I get it at first. This means at this location, I have this pattern. Okay. So it gives me this value. Again, this is also 3. So it is able to find where this value is maximum. That means you have those kind of features there, which match with filter 1. For each filter, we do it for the next filter. And this is called the feature map, which you get from the convolutional layers of your deep learning neural network, CNN. So this was a 6x6 image, and if you have two filters, you are getting this feature map. And now the size of this feature map is 4 into 4 into 2. Right? So these were 6 into 6, 36 values. Now you have 4 into 4 is 16, 16 into 2, you have 32 values. If you have 3 filters, that means 4 into 4 into 3, that will give 36. If you have 4 filters, you will get more feature maps. If you have RGB channel, that means then you have 3 2D matrices, one representing red, green, and blue. So in that case, you have basically 3 images, and for each of these images, you find further the feature maps. So and you get multiple features. And finally, fully connected means all these neurons are connected, all these inputs are connected to all the neurons in the next layer. Okay? And flattening means you are making it into a 1D. So now what is being happening out here is, do we really need a fully connected? That will increase the number of parameters. And so they've tried to show if we can reduce it, only connect 9 inputs, not fully connected. No? For finding it out, we just need to connect these 9 values, not all the values in the image. So that is what is being. So we have fewer parameters. Even the same thing for -1, the same thing for all of these. So we don't need to connect. Now in this case, they are not fully connected. So first 3, then from the next row, the next 3 values, next row, next 3 values. Same for filter 2. 3 values from row 1, 3 from 2, 3 from 3. So these are now not fully connected. So we have fewer parameters out here. So we have shared weights, you can see. So in this case, the coloring is same. That means they are using the same weights here. For computing this value and computing the next value, the same weights are being used. The weights are shared and it is not fully connected. So it is reducing the number of parameters. So if we see the whole CNN model, many times you must have seen that this deep learning models, there is some 2D input. Mostly it is being used for images. And then you have convolutional layers. In between the convolutional layers, you add max pooling layers. And again, convolutional and max pooling, these will be repeated multiple times. And then the final will be a flattened layer, which is fully connected, and you get the output. Okay. So what is max pooling? So from filter 1 and filter 2, you got certain values. So now we know that the pattern is there, the maximum value is there. Right? So instead of considering all these 4 values, I can divide the whole feature map into 2 by 2 sub images, you can say, or sub features. And from this, instead of considering all the 16 values, I can just consider 4 values. From the first, I will take the maximum. From the second, I will take the maximum. Same for third and fourth. So I take only the maximum. So the redundancy is reduced. So it is some kind of a subsampling. So will not change the object. Okay. So subsampling हम images में वैसे भी करते हैं कि I have a large image, I subsample it. The simplest way is I'll consider 1 pixel, I'll leave 1 pixel. overall, it will show me the same thing, but some finer details will be lost. So we can subsample the pixels to make images or data smaller, and redundancy is reduced, but the overall working remains the same. So it leads to reduction of parameters. Otherwise, the complexity of the system will further increase. So we need fewer characteristic parameters to characterize the image. So in the same way, CNN will compress it. Just hello. Hello.
Yes, ma'am.
Haji, I just got an important call. I was calling. I'll continue. So we reduce the number of connections by doing this. Again, max pooling. We have shared weights. We've seen. Okay. So first off, instead of fully connected, we are having specific connections. We are reducing them. Then weights are shared. Same weights are used at different parts of the image. Next is max pooling or median pooling, or you have different pooling algorithms which could be used as per your requirement. It further reduces the complexity. So now we have a 6x6 image, and now we have, based on the number of filters, we have 2x2 images or feature maps which we can use further. So we have newer image, but which is smaller in size. Now we can further convolve it to get more features. Again, apply max pooling, and these steps are repeated multiple times. So one layer is convolutional, then again pooling layer, again convolutional layer, again pooling layer, and finally we have a flattened layer. So each filter is a channel, we can say. So here we get a new image. Again, it is convolved. And again, pooling. And finally, so each time we get a new feature map or a new image. And now this new image is smaller, and it has only very less redundancy, only the required feature maps which are there, which will help us to differentiate between different classes of images, classify them or recognize some objects. And then the fully connected layer is trained. So now flattening. Right? So now finally we had 2D images. Now those feature maps are flattened into a 1D data. And this 1D data is given to a fully connected neural network, and the weights are trained to get the final output. So previous to the deep neural networks, what we were doing is we were using multi-layer neural networks. But even if I have a small image of 100 by 100 pixels, that means there will be 10,000 pixel values in that. So if I want to use it with neural networks, and I don't want extract any feature from the image, I give it as such. That means my input layer neurons should be 10,000. And those 10,000 neurons are connected to the next layer, that may be the hidden layer. And maybe in that I have 1,000 pixels. So 10,000 pixels connecting to 1,000 pixels. And finally, in the output, maybe I have 100 different categories of images, or 128. To represent 128, I need at least 7 output pixels to define them. Like 000 means for first class, 00001 second class. So 2 to the power 7, 128 output pixels, 7 output pixels I require. So that leads to a lot of calculation. So normally what was done previous to deep neural networks was, from these images, from this 2D data, we extract some features, and these features are given to the neural network, which are smaller in size. Maybe I extract the histogram of the image. And if my grayscale image is there, there are 256 different shades. So I can have 256 different values in the histogram representing how many pixels of a specific color or shade are there in the image. So instead of 10,000 pixel values given to the neural network, I'll give the histogram. So in this also, we flattened it finely when we have extracted only the useful information. And then with these features, we train the weights to finally classify it. We give it to the fully connected neural network. So this was in brief about the deep neural networks. And now I'll just show you one program where you can use PyTorch with all these concepts. So I'll share the other tutorial, or I'll directly share the program only. I'll just show you. Just a moment, I'll open it first. So is this program visible now?
Not yet, ma'am.
Okay. So I think now it is visible.
Yes, ma'am. Now it is visible. CNNPT.py file.
Yeah.
Thank you.
So you people have implemented some programs in Python? So in this case, what we have to do is, first of all, we need to import some libraries. Like we import Torch, we import torch.nn neural networks as NN. We import Torch Vision also. We import Torch Vision.transformers as transformers. So we need to import. And now it depends if you're working on a GPU-based system or a simple CPU-based system. So if you don't have a GPU, you will put a 0 here, and it will normally work on a CPU system, normal desktops which we have. So in this case, I set some parameters here, which are called the hyperparameters, number of epochs, how many times the whole training process will be repeated, and number of classes which I am considering, maybe 10. Batch size, each class has 100 input images, you can say, and I consider a learning rate. So whenever you're changing the weight of a neural network, like in if we see backpropagation, so we have delta, that is basically the difference between the target and the original. We multiplied it with out 1 minus out, and we have a eta, which is called the training rate coefficient. So what is the purpose of training rate? If we change the weights by large amount, sometimes the weights will become less than required, or they will become more than required. So we need to change the weights in small steps. And when we change it in small steps, it will reach the global minima for the error, gradient descent. So all those concepts are there. So in this case, we have kept the training rate as 0.01. So in this case, they also do it like that. Initial steps, they'll keep it larger so that you reach closer to the global minima. And out that you start changing the weights by a small amount so that they reach the best weights. Okay? So there are many data sets which are available through PyTorch also. So Torch Vision data sets. So this is one specific data set which we are considering, MNIST. And this is how we can download the training data set. So in this case, we are putting train is equal to true, transform dot two tensors. So multidimensional, like in NumPy, we have multidimensional arrays. In this, we have multidimensional tensors in which we can store our inputs and outputs. In the same way, we have test data set. From the same, we are considering some part of it as test, and then train and test, both data sets are given. So you can load those data sets by using specific functions which are there in the data set. So once you get the data set, now you need to define your convolutional neural network. There are standard like VGG16, VGG19. They have specified number of convolutional layers, max pooling layers, flattened layer. In this case, you can also design your own convolutional neural network. You can specify how many convolutional layers you want, how many max pooling layers you want, which kind of activation function you want to use with it. So in this case, we want to consider, we generate an object. There is a class connet, and this is neural network dot module, and there are number of classes 10. And there is a superclass from which we inherit different classes. So in this superclass, what we are doing is layer 1, neural network sequential. And in this, we are considering convolutional layer, and we are specifying the parameters like padding, we require it or not, stride, kernel size, which we want to use. And in this case, we are using the size which we are going to use of the image and all those things, number of input and output neurons and all those things. And then this is for normalization of the values, 2D values, and activation function which is used is ReLU here. Then you want to use a max pooling layer with the kernel size of 2 and stride of 2. In the same way, you have the second layer. Again, there is one convolutional layer, and there is this kernel size and stride and padding. So again, batch normalization, which is there, max pooling, and then fully connected layer. This is basically linear neural network. And now your size is 7 into 7 into 32. This will be the total size of the flattened layer which we get. So kernel size is 5, and we are using 32 such kernels. So, and your image, then this is basically layers you are defining. Now you want to define the forward pass. So in this case, self dot layer 1 x, self layer 2 output. So you're passing the input to layer 1, then you're getting output from layer 2, and then you reshape that output into a 1D, and then you give it to the fully connected layer, and then finally it will return you the out. So, and then you basically what you're trying to do is you want to there will be a learning rate which will be there, and there will be some criteria to find the loss and optimize it. So actually it was a very brief, you can say, lecture. So I couldn't discuss all these things. So there will be some criteria for optimizing so that reducing that loss value. So all this is for optimizing, and Adam is one of them. And there is some learning rate, and then you train the model, and it will have 2 passes. like I've said, forward pass when you give the input and you get output. Then in the backward part, the desired output and the actual output, their loss is calculated, ki how much difference is there between the two, and based on that the weights are retrained in the backward pass. Like we trained first the weights between output and hidden, then that hidden layer, then and the next hidden layer, and so on. And epochs number of times this process will be repeated, and finally when you get a model which is trained, so you can have a different criteria for stopping. So it could be number of epochs, the level of error which you are ready to consider it as acceptable when it minimizes and it doesn't change any further. And then model dot evaluate. So evaluate mode, you want to now test this trained model. So again, you load those test loader and images to, and the images and their labels are being taken, and you pass that images to the model and you get some outputs. And now, because we know the labels of those images, I know maybe this image belongs to the alphabet A, this belongs to B, and then I will see ki how many times it has predicted A as A and B as B, and vice versa, ki how many times it has misclassified it. Based on that, we are going to find out the test the accuracy of the model. Okay? And so you calculate the accuracy, and based on the correct predictions and the total predictions which were there. So you have two positive and false positive, two negative, false negative, and so on. So based on that, you are going to find, or you're going to predict. So this was just a very generic code with only two. So you can have large number of layers here. You can change this activation function. Instead of max pooling, you can have different pooling algorithms which are there. And you will decide how many convolutional layers you require for a specific problem. So in this way, writing, if the same program is written in C, maybe it will consider of 100 pages, right? So everything is being done for you. So you just need to know okay, which function, what you need to use to develop a overall, you can say, deep neural network. So a small program will help you to designing your own, or you can use an existing deep neural network also. So this framework is quite capable of doing that. So I will just have a 2-minute break. I'll just have water, and then we can take up the questions if there are. In the same way, you can write your own small programs also. You can do the programming as you do in C and other languages. So this is a small program which will explain to us what we had already done. Like I have these 3 inputs, and for these 2 inputs, I want the output should be 1. And for one of them, I want it to be 0. So this is my input, this is my desired output. And the function, activation function, which I want to use is sigmoid. So I define the sigmoid function here. And then I define the derivative of the sigmoid, that is return x into 1 minus x, where x is the input to this derivative sigmoid function, that is the output which is coming from the previous layer. So I can set the epochs. I've set it at 7,000 for training. Learning rate is 0.1. Input layer neuron X into shape of 1. So that is very important. How many neurons you will have in the input layer and the output layer will depend on your problem. Like here you have 4 neurons in the input and you can have only 1 neuron in the output because your output is either 0 or 1. So here hidden layer neurons, we want to keep them 3. Output neuron is 1. Weights and bias initialization, like I've said, initially we take the random weights for the input layer, for the hidden layer, for the output layer. So forward propagation is hidden layer input 1 torch.mmx into WH, weights into the inputs. So this is how which we first layer we have the input and the weights, then hidden layer activations and W out, and B out is the bias which is there. And this has 2 passes. The forward propagation is only when we give the inputs and we get outputs. And so when we get the output, then for training it, we want to compare the output with the actual output, which is there, y minus out. And then we take the derivative of the sigmoid. And then we want to find out the slope for the hidden layers that will be based on hidden layer activations into that we will give it to the derivative of the sigmoid. So this is the final output. This is the corresponding outputs for the hidden layers. And so D out is E, that is the target, minus out into the slope of the output layer. So once you get this slope for the output layer, this can be used for finding the error at the hidden layer. That is D out and dw out dot t. So D hidden layer is error at hidden layer into slope of it. So slope we are able to calculate. Error we are computing it indirectly by propagating the error from the output layer to the hidden layer. And then we find the W out and the bias output. That also needs to be trained. And the changes are, and then we finally get the next iteration weights for bias and the different layers. And then we can predict actually what we are having and what is being predicted. We can see that. So this is how you can write your own small programs, your own neural networks also. And you have inbuilt where all those layers are there, and you just have to choose how many convolutional layers you want, how many pooling layers you want, how you want to use the flattened layer, which classifier you want to use with the flattened layer, and all those things. So now I'll have water and then we'll have a So you can just drop if you have so there are different messages which some comments I'm getting. So if you have any questions, you can ask me, or you can just drop me a message, or you can start trying by using Colab, or if you can install all the libraries on your system and you try to run. I'll share some small programs with all of you. which you people can just use. And if you have any errors or something, you can just drop me a message. I'll try to help. So any questions are welcome if you have any questions.
Dear participant, the session is open for discussion. If you have any question, please feel free to ask. You are permitted to unmute your mic.
Very good morning, ma'am.
Haji, good morning.
Okay, I have one query, ma'am, that if we want to create a graphical user interface by using this PyTorch, what is the coding for that, ma'am?
See, I haven't tried the graphical user interface with the PyTorch. But if you want, I can just go through it and I'll just let you know. The
Okay.
coding will be very brief in that case. It won't be very.
Yes, ma'am, because I only want to display the image, the result image, and you can say one input image and the output image, and the backend coding. I will do the connectivity. This much
Okay.
only I want.
Okay, so you just want a graphical user interface key. You want to display your input image, and the same way you should get your output image.
Yeah.
So that can be done. I think I'll just check the plotting part. We had done it, and I'll share it. You can just drop me your email ID. I'll share that code with you.
Okay, ma'am. I'm just dropping it in the chat box. Thank you so much. Thank you.
I'll just check.
Amandeep, ma'am.
Haji, sir.
Ma'am, please provide all the entire content which you present here so that we can upload all the content for the participant. Since
Okay.
This is an online session and after this
They'll practice it.
required to practice on it. So this will be very helpful to all the participant. And if we have some more model which can assist to the participant, it will be very nice help and support to the entire participant.
Surely,
we provide
sir.
all this content through their email address, and also we will upload all this content on the portal where all the participants are registered. So all the things will be very accessible to each one.
Surely, sir. I'll be doing it. Maybe
Yes,
tomorrow late evening or today late evening or tomorrow morning. Because there were some files which were pending. So next half I'll be working on them, and in between I'll share.
Thank you, ma'am.
Haji, sure.
Participant, if you have more question, please feel free to ask. President Morotolo is there. Actually, ma'am, your session was entire
just before lunch.
Yeah. Very
No
nice
problem, sir.
presentation.
Yeah,
And
I
people
can
are
understand.
very
Actually, sir, these topics are very, very vast. So
yeah.
I can understand the participants because maybe they have different levels. They're working at different levels. And
Yes,
there are many things which we need to include. And any questions in future also are welcome. So if they have any doubts or anything, they can just get in touch.
Ma'am, kindly share your email ID.
Haji, amandeep.kaur. I'll just share it. I've taken yours. So this is the email ID. So
okay, thank you so much. Yeah, thank you.
Haji. Okay.
Kirti, over to you. Please proceed.
Thank you, sir. Thank you, ma'am, for such an interactive, informative, and incredible piece of information. It was really a wonderful session, ma'am. It added too much to our pre-existing knowledge. Now I invite Dr. Durvesh Kumar Verma, sir, for formal vote of thanks. Over to you, sir.
Thank you, Kriti. On behalf of organizing committee, I would like to thank Professor Amandeep Kaur for who spared time from her busy schedule to grace the occasion. Today we had opportunity to hear you, ma'am, your
Thank you,
views on neural network and deep learning. The session was very informative, engaging, and thought-provoking. This will surely be going to encourage us for in our future events. Thank you, ma'am.
Thank you, sir. Thank you so much. So I leave, sir, then.
I also
Now I request Dr. Durvesh Kumar Verma sir to present e-memento to today's speaker as a token of appreciation.
ma'am has left, I think, ma'am.
Might be there is network issue from there. I think ma'am has left the meeting.
Ma'am has left. So this is the
Yes, I have done from me, sir. I have done.
Okay, sir. So finally, I would like to thank all of you for attending today's session. Your participation and engagement have been greatly appreciated. As we come to the end of this session, we would like to express our gratitude to all the participants for their active participation and insightful contribution. We hope that you found this session informative and engaging. We hope that this program has been beneficial to you and that will contribute to apply the learnings in your work. We wish you all the best in future endeavors. So tomorrow we will meet at the same time for the next session. Thank you all and have a great day. Dr. Meerjan sir, can we leave the meeting?
Yes, we can do now.
Once again, thank you all.